Welcome to section 334. So previously, we've learned to find the real zeros of polynomial functions of degree 2 and higher. We've also learned to find the complex zeros of a polynomial function of degree 2. So now we will find the complex zeros of polynomial functions of degree 3 or higher. So a variable in the complex number system is referred to as a complex variable. A complex polynomial function f of degree n is a function of the following form, f of x presented here, where our a sub n minus 1, a sub 1, a sub 0 are all complex numbers, where a sub n does not equal 0, n is a non-negative integer, and x is a complex variable. So as before, a sub n is called the leading coefficient of f. A complex number, r, is called a complex zero of f if f of r equals 0. So we've learned that some quadratic equations have no real solutions, but that in the complex number system, every quadratic equation has at least one solution, either real or complex. The following theorem is so important and useful that it has become known as the fundamental theorem of algebra. The fundamental theorem of algebra states that every complex polynomial function f of degree n greater than or equal to 1 has at least one complex zero. Note, it's important to understand that a complex zero may be a real zero or a non-real zero. Okay? So every complex polynomial function f of degree n greater than 1 can be factored into n linear factors, not necessarily distinct, of the following form, where a sub n are 1, 2, and r sub n are complex numbers. That is, every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. Okay? Which is why the theorem states that it's not necessarily distinct, meaning different, not the same. Okay? Remember, n also represents the degree of your polynomial. So if you know the degree, then you also know the number of complex zeros. And remember, complex zeros could be real or not real. All right, objective 1, use the conjugate pairs theorem. So the conjugate pairs theorem states that suppose f is a polynomial function whose coefficients are real numbers. If r equals a plus b times I is a zero of f, then the complex conjugate r bar equals a plus b times I. Oh, that's actually minus. It's a conjugate. And the regular wouldn't be the same. A minus b times I is also a zero of f. So in other words, for polynomial functions whose coefficients are real numbers, the complex zeros occur in conjugate pairs. So once we know a complex number is a zero of a polynomial function with real coefficients, then we know its conjugate is also a zero. So a corollary, or like a subset of the theorem, states that a polynomial function f of odd degree with real coefficients has at least one real zero. So if your polynomial function's degree is an odd number, then we know that there exists at least one real zero. So in our example, we have a polynomial function of degree 5 whose coefficients are real numbers, has the zeros 2, 4i, and 3 plus I, and we're asked to find the remaining two zeros. Okay. So we know right off the bat that 5 is an odd number, so our degree is going to have at least one real zero. Okay? Now, the real zeros that our problem tells us are 2, 4i, and 3 plus I. Okay? And we're asked to find the remaining real zeros, all the remaining 2 real zeros. Okay? So if our zeros are 2, which is real, 4i and 3 plus I, which are non-real, but they're all complex zeros, we know that if we have a non-real zero, its conjugate will also be a 0. Okay? So its conjugate is going to be negative 4i and 3 minus I. And those 2 would be our remaining 2 zeros. Okay? So again, our polynomial has a degree of 5, which is odd, which means we have at least one real zero. And our one real zero is 2. Now we have non-real zeros as well, 4i and 3 plus I. Since these are non-real zeros, we know that their conjugates are also zeros of this polynomial. And those conjugates are negative 4i and 3 minus I. Okay. Objective 2, find a polynomial function with specified zeros. So for this example, we're asked to find a polynomial function f of degree 4 whose coefficients are real numbers that have the zeros negative 2, 2, and 3i. So if the zeros provided to us are negative 2, 2, and 3i, we also know that 3 plus I is also a 0 of this polynomial function. We know that our polynomial function is a degree of 4, so we are going to have x to the 4th present in our polynomial function, and that is going to be the highest degree. Okay? So now that we have our zeros, we can identify our factors associated with those zeros. So for negative 2, we would have x plus 2. For 2, we would have x minus 2. For 3 minus I, we would have x minus 3 minus I. And for 3 plus I, we would have x minus 3 plus I. Okay. So now we can simplify this. X is going to equal x plus 2 times x minus 2 times x minus 3 plus I times x minus 3 minus I. Okay. All right. So I would like to group together these, first two. Oops, I'll change the word to this. I'm going to group together the first 2 terms. I'm going to change it like it's actually right here, just so that you can see it a little better. We'll group together these 2 terms. There we go. Okay. So now I can multiply. So we'll have x squared minus 4 times x minus 3 squared minus I squared. Okay, so if we were to do FOIL and we multiplied these first 2 binomials and then multiplied these 2 binomials, we would get the following binomials. Now, this also is a formula for the difference of squares that says a squared minus b squared is a minus b times a plus b, okay, which both of these sets represent. Okay? So now we can multiply this out. All right, so we still have our x squared minus 4. And over here, we're going to have our x squared minus 6x plus 9. That's what x minus 3 squared is. Minus I squared, and I squared equals -1. So we'll be subtracting a -1. So simplifying, we get x squared minus 4 times x squared minus 6x plus 10. Now we want to multiply this all the way through, so we'll have x squared times x squared, which is x to the 4th, and then we'll have negative 6x cubed, then a positive 10x squared. Then we'll multiply everything by -4, so that's negative 4x squared, and a positive 24x, and then a negative 40. So I first multiplied everything in this quadratic, I guess you could say, all the terms in the quadratic by x squared, and then I multiplied everything in the quadratic by -4. Okay? So now we can combine like terms to get our polynomial function, which is x to the 4th minus 6x cubed plus 6x squared plus 24x minus 40. And that is our polynomial function f of degree 3. So every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors or irreducible quadratic factors. Okay. So that's something to keep in mind when you are given a polynomial function and you now want to find its complex zeros, which is exactly what we're doing in Objective 3. Find the complex zeros of a polynomial function. So the steps for finding the complex zeros of a polynomial function are the same as those for finding the real zeros of a polynomial function. Okay, and so we're going to go through those same steps here in this next example. So find the complex zeros of the polynomial function of f of x and write f in factored form. Okay. So for step number 1, we need to determine the degree and the maximum number of zeros that are present in our polynomial function. So this polynomial function has a degree of 4. That's the highest power. Okay. So that means f has a maximum of 4 complex zeros. Okay. So for step number 2, we now need to determine the total number of positive or negative complex zeros that are present in this polynomial function. Okay. So for f of x, we need to determine the number of sign changes, which will give us the number of possible positive rows and rows. So one sign change here, one sign change here, and one sign change here. Oh, and one sign change here. Look at that. So we could have 4 or, and we just keep subtracting 2, 2 or 2, oh, not 2, or 0, or 0, positive real zeros. Okay. Then to find the possible number of negative zeros, we're going to change the sign of each term that has an odd power. Remember the first one, the second one is going to change. The third one stay the same. Fourth one will change. And stay the same. Okay. So all of these terms are now positive. So there are 0 negative zeros. All right. Okay. So now for step 3, we need to determine what these potential real zeros are by looking at the leading coefficient and constant term. So our constant is a sub 0, which is 20. So that's P. Our leading coefficient is 2. So that is Q. So we now want to take the factors of P divided by the factors of Q. So the factors of 20 are 1, 2, 4, 5, 10, and 20. And the factors of 2 are 1 and 2. So that makes our possible number or possible zero values. 1 divided by 1 is 1. And then 2, 4, 5, 10, and 20. Now I'll divide everything by 2. So we could have 1/2. 2 divided by 2 is 1. 4 divided by 2 is 2. 5 over 2. 10 divided by 2 is 5. And 20 divided by 2 is 10. So these are the possible zeros for the problem. So now we need to test out a 0 to see if it is potentially a 0 for. So we're just going to choose one to help us. We are going to choose, let's choose 1. Start and see if it works. Okay. So we'll list the coefficients in descending order. We have no missing terms, so we know there's going to be a coefficient for each slot. So we'll have 2, negative 11, 13, negative 44, and 20. We want the remainder to be 0, because if it's 0, then we know that 1 is a 0 of this polynomial function. So we'll bring down the 2 and then multiply. Then we will add. And we'll multiply. Then we will add. Then we'll multiply. Then we'll add. Then we'll multiply. And then we'll add. Okay. So we see here that 1 is not a 0. So then we'll choose another number. Okay. So let's choose 5. Okay. So for 5, put this up. Place in our coefficients. Okay. Then you can choose any number from that list. So bring down the 2, multiply, add, multiply, add, multiply, add, multiply. Oh yeah, 5 is it. Okay, so our remainder is 0. So we know 5 is a 0 of our polynomial function. And our quotient is going to be the depressed polynomial 2x cubed minus x squared plus 8x minus 4, and the remainder 0, which is awesome. So now we have f of x equals x minus 5 times 2x cubed minus x squared plus 8x minus 4. Okay, so we've started the process of factoring our polynomial function. So now back to our quotient, right? Can we factor this function? Okay, well, since it is a 4-term function, we can utilize different methods in order to factor this polynomial. You can continue with synthetic division and see if another number is divisible by this polynomial, or we can use other factoring methods like factor by grouping. So if we take 2x cubed minus x squared plus 8x minus 4, group together the first two terms, group together the last two terms, take out the GCF in the first two, which is x squared, we're left with 2x minus 1. Take the GCF out of the second two terms, and we're left with the same binomial, 2x minus 1, which is the goal. So now we can take the GCF out of these two terms, which is 2x minus 1, which leaves us with x squared plus 4. Okay? So now that this function is factored, we can set both of our factors to 0. Okay, and solve for x. So in the first one, we'd have 2x equals 1 dividing by 2, x equals 1/2. In the second one, we'll have 2 or x squared equals negative 4. So x equals plus or minus the square root of negative 4. So x equals plus or minus 2i. Okay? So now we have f of x in a complete factored form of x minus 5 times 2x minus 1 times x minus 2i times x plus 2i. Okay? And this 2x minus 1 is the factor, the linear factor that got me the 0, x equals 1/2. So it just went up here to its linear factor. So for the linear factors that contain the imaginary values or the complex values, we can also rewrite it as x squared. So we can write f of x as x minus 5, 2x minus 1 times x squared plus 4. Okay? Both of them are correct depending on how your problem wants you to write out your function. Okay, and so this would be our final answer. All right, and just to conclude this problem, let's state the 4 complex zeros. Of f are 5, 1/2, 2i, and negative 2i. So those are the 4 complex zeros of our problem. Excellent. That concludes section 3.4.